Good evening, everyone. Welcome to the fifth simulation training session today. Today, we will be covering centralized HVAC systems and cost estimation. Our experts will elaborate on the metrics for cost estimation and explain how you can use data from your project to make the right decisions about the system selection. We will also see how to use Design Builder to model centralized systems for energy efficiency. Before we begin, I would like to thank the Department of Science and Technology, our program supporters, affiliates, and CSR supporters. A special thanks to Design Builder for their continuous support to SDI. Today, we have with us Mansi Parekh and PC Thomas. Mansi Parekh is a senior sustainability consultant and has key qualifications in the field of passive design, low energy cooling, and HVAC systems. She has worked on various projects with goals leading to net zero energy, water, and waste. We also have with us PC Thomas today. PC is the founding director of Team Catalyst and also an adjunct associate professor at the University of Sydney. He specializes in integrated building design, using simulation tools to assist in the design and delivery of sustainable buildings, in particular in predicting the performance of mechanical services. He has a master's degree in mechanical engineering, 30 years of consulting, research, and teaching experience in sustainable buildings, building energy simulation, energy auditing, energy efficiency in buildings, and solar energy. PC is talking to us from Australia today, so it is late evening for him right now. Hi, PC, and hi, Mansi.
Hello, hi.
Hi. Hi, Mansi, we'll start with your presentation first.
Sure.
So you could go ahead and share your screen.
I'll start sharing my screen. Hello, everyone. Can you see my screen, Yashima?
Yes.
Perfect. Okay. So, energy efficient buildings are often taken as they are going to be, they are perceived to be cost costly or say expensive. However, if designed in a right way, there is not much cost difference where you would see that. And since they would be saving in annual electricity cost and first cost of the HVAC systems, that we'll be discussing in today's webinar. In this webinar, we'll be also covering topic of net incremental cost and information which we can get from a particular energy model. So we have a question here. So Yashima, can we start the poll?
Yeah. All right. Our first question for today is, which according to you consumes most energy in an air-conditioned building in a hot and dry climate? And your options are indoor lighting, equipment like PC or laptops, and the third option is space cooling. So you can go ahead and start putting in your responses, and we'll discuss them in a while.
So, different typologies of building would have a different energy consumption numbers or end use energy use. For say for office building, it would be different. It would be different for schools, hospitals, etc. Here we are considering say office building. Then what would be the split look like?
All right, I will now go ahead and end the poll. We have sufficient responses, Mansi. Yeah, are you able to see the responses?
Yes, I can see the responses, and maximum people have given 80% of them had said space cooling, which is the correct answer here in this case, because I'll show you how in the upcoming slides. So, in this chart, as you can see, that this shows the annual energy consumption split. So this is for a typical office building in Visakhapatnam. And as you can see that cooling accounts for maximum energy consumption, which is 44% here. and followed by equipment and lighting, which are roughly around 26 and 22%, and fans and ventilation, which accounts for 88%. I mean 8%. So I would say, as I said earlier, this would be different for different kind of buildings. There are IT offices which would have higher in terms of equipment loads and equipment consumption. So and these are the kind of data which we can get from energy model, like what will be the electricity consumed in a building. In this case, it is roughly around 8,29,824 units. This is the data which we can get from energy model. And based on that, so say for this particular case, the electricity cost per unit in Vishakhapatnam was roughly around 10 rupees per rupees per unit. So the annual electricity cost will be around 83 lakh here, which you can see the number in blue. So this is the kind of data which we get from energy model. Apart from that, we can also get peak cooling load. So for this particular building, it was roughly around 200 TR. So when we look into square feet per tonnage number, it was coming around 292. And we can also get information like unmet hours. So unmet hours here was 160, and these are the hours where the even after providing HVAC systems, the space is not able to meet those set point temperatures which we assign to. So, when we talk about energy efficient buildings, the first question which we often get asked by developers, architects, or any client is that what is the additional cost for energy savings, or says what is the additional cost which they'll have to pay, or the energy savings they'll be getting by incorporating these energy conservation measures. So here is how we have calculated annual energy savings for insulated roof measure. So in this graph, the y-axis shows annual electricity bill in INR, and the x-axis shows three cases. The base case is the case where we have no insulation. The case 2 is the roof where the roof insulation is 0.9 watt per square meter, which will require roughly around 15 mm of insulation. Case 3 is the U value of 0.4 watt per square meter Kelvin, which would require roughly around 25 mm of insulation. So, and these are sort of numbers which we get in terms of energy saving. So by providing U value of 0.9, we can get annual savings of 1.6%. That would translate to 1.3 lakh savings in terms of annual electricity bills. That that number for U value of 0.4 is roughly around 1.8 lakh rupees. This is annual saving in electricity bills. These are the other energy conservation measures for envelope, which I also checked for this particular project in terms of annual electricity savings. This include insulation for walls, where I have checked for wall insulation of, so say it starts for U value of 1.7 to 2.2. That is for a typical brick wall. Then we further reduce it to U value of 0.22, which is the number which we get from Energy Conservation Building Code. So ECBC 2017 version, ECBC super numbers. Similarly, I have checked for various roof measures, various glazing, energy efficient glazing measures. Here you can see various starts with single glazing to DGUs with high with say lower SHGC. And then I've checked for various shading devices, which would have 0.3 meter overhang to overhang depth of 1 meter or so. So these are sort of measures which I also checked, which we generally do for each of the project. So this is a detailed study of energy conservation measures for the roof. Okay, earlier we saw 3 cases. Here we have detailed it out. So on x-axis, you can see annual electricity savings in rupees, and on y-axis, you can see energy conservation measures. This is the base case with no insulation and the U value of 0.2. So as you can see, the lower the U value, the higher the amount of insulation it is required. So say, to put this in perspective, U value of 0.9 will require insulation of roughly around 20 mm, and say U value of 0.2 will require insulation of 125 mm, which is going to save around 1.8 lakh rupees annually. However, 25 insulation will require extruded polystyrene insulation if we go. That would cost around 250 rupees per square meter, while 125 of insulation is going to cost you 1250 rupees. So there is a significant difference in the amount of cost which would be required for both of putting this together. So there has to be a balance between annual electricity cost savings as well as cost of incorporating energy conservation measure in a building to arrive at a decision to which insulation should you suggest to the client. So that's the reason we have a term called net incremental cost. So, cooling accounts for maximum of energy consumption in the building. That's what we saw earlier. Further, it also adds significant cost of equipment in a particular building. So there would be a cost attached to a 200 tonnage of chiller or say 500 tonnage of chiller. There will be difference in both of those costs. So for example, if I give you 1 ton of even split unit, which you have in your households, so that will cost around 25,000 rupees, while a split unit, what for 2 tons, okay, that is going to cost you around 40 to 45,000 rupees. So there is a significant difference in the cost of both. So in last webinar, we saw that energy conservation measure has a significant impact on cooling loads too of a building. So say, for example, what we saw earlier in the last webinar was that glazing of U value 2 as compared to, single glaze with U value of 0.5 would reduce your cooling load by roughly around 15 to 20%. So that is going to be your savings in HVAC system sizing. So while calculating the cost of energy conservation measure, it is important to account for reduction in the cost of HVAC system. So for this, we have a term here. It is called net incremental cost, which is difference between incremental cost of the ECM, which includes cost of labor and material, and cost reduction in HVAC system because of cooling load reduction of that particular ECM. So here is how we account for cooling load reduction and in turn reduction in HVAC system size. Here is the example. So in this graph, y-axis shows the roof ECMs, again the same measures which we have seen earlier, and then on the x-axis we see the tonnage of refrigeration which would be required for each of these measures. So here you can see that for base case without any insulation, you would require 180 tons of refrigeration. However, when we have insulation and achieve U value of 0.9 for the roof, we can get savings of 8 TR. Okay. However, for the case with U value of insulation 0.2, we can get that system sizing reduction by almost 15 TR. So in this graph, here shows the net incremental cost of roof measures. So in this graph, y-axis shows roof U values and x-axis shows the cost. Okay, and the bars in green shows cooling capacity savings due to reduction in system sizing, and bars in blue shows the incremental cost. And the difference between both is called net incremental cost. Okay, so for U value of, say, for example, U value of 0.2, okay, so the net incremental cost is roughly around 6.1 lakh rupees, because this is energy savings, cooling capacity saving, and this is the incremental cost of the ECM. So this is the net incremental cost. So in certain measures, for this one, the net incremental cost is negative. That's interesting, right? So in this case, why it is negative? Since the cooling capacity saving due to reduced system size exceeds the cost of insulation. So that is the reason we have negative net incremental cost. So you can tell client that these measure actually reduces the cost of construction of that particular building. So in order to calculate incremental cost of roof of a particular U value, you require two things. First is the cost of material. Okay, and the second would be the cost of labor. So the first, for this, what I did was I did a market survey, reached out to various roof insulation. I started looking into various roof insulation like XPS, EPS, Rockwool, and contacted companies like Dow Jones and Owens and Corning to get these numbers, and then multiplied that by the area and added into the labor cost. So that is how you do the cost calculation. This would be different. However, the cost calculation would be different for each of the ECM. And this is sort of important information which we can get from an energy model. So when I do cost calculation and area calculation, I generally refer to energy model directly. I don't have to go to my drawings to check the areas. So this is the list of information which you can actually get from an energy model, and it would be very simple. So information like area of rooms and total area of building, this can be helpful for EPI calculations. Area of wall, roof, and glazing, this can be helpful for calculation of cost of insulation. So incremental cost of insulation for walls or roofs, or you can start looking into glazing cost as well. Cooling capacity savings or HVAC system sizing. This information can be helpful to determine and select the correct HVAC system with the right tonnage. And say for example, if you are doing water calculation, water consumption for cooling tower and evaporative cooling, we can get that also from energy model. Now, resiliency is an important part. So say if there is a grid independent solar PV system and you want to calculate the battery capacity for the same, you can get that information also from energy model by using various end uses at the time of the day. Here, I'll show you how. So this information was used. So on this chart shows typical energy use for a summer day. Y-axis shows energy consumed in an hour, and X shows the hour of the day. The lighting and equipment, which we can see in yellow and yellow ochre, are mostly constant. So mostly constant during the unoccupied hours as well as the occupied hours. We have a certain number to it. And the ones in red are the cooling consumption, and those are basically changing, or those are fluctuates based on the time of the day, occupancy, as well as outdoor temperatures. So say for this is a mixed mode school building where classrooms are only conditioned for 4 months of the year. Okay, mixed mode means they for some months they are conditioned, for the other months they are not conditioned. So here the solar PV battery installation capacity would be constant for constant load. So say for only lighting and equipment. So this is sort of information which we can derive. So after we work for energy efficient envelope, we start looking for on right sizing of HVAC system and selecting the appropriate kind of system. These are energy conservation measure which I worked on for this particular building. And there are two kinds of HVAC systems. One are the centralized and the other are the decentralized system. Centralized systems are the one where you have multiple indoors connected to one outdoor, or say I would say one outdoor facility. So that can be your variable refrigerant flow systems or your variable air volume systems with your outdoor chillers. That can be air cooled chillers or water cooled chillers. And your the decentralized systems are nothing but your split ACs. Those are the examples. So your split ACs at home, they have one particular indoor unit and connected outdoor unit. So those are called decentralized system. So these were all the systems which I simulated for this particular building to understand which we will go for, which we would suggest to the client. So Yashima, we have a question coming up. Can you start the polls?
Yeah. All right.
Yeah.
So our second question for today, I have just launched it. So the question is, which from the below list, according to you, will be efficient HVAC system for an air-conditioned office space where area is 10,000 square meter? And the options are split AC system. Second option is air-cooled VRF system with a COP of 4.5. And the third option is variable air volume system, also known as a VAV system with water-cooled chiller, where the COP is 6.
Yeah. So I would like to, again, I would like to repeat myself. Split AC systems are decentralized system, one air outdoor, one indoor. While VRF and VAVs are centralized system. And COP means coefficient of performance. Also, I would like to give there's a note here. So, different HVAC system types are covered in mechanical HVAC and low energy cooling SLMs. So I would request students to go through those that in detail before starting the energy modeling of different HVAC types. So please
Right.
go through that. Yeah.
Thanks, Mansi. I will now go ahead and end the poll. Um, Here are the results, Mansi.
Perfect. So I think maximum people have said here that variable air volume system with water cooled chiller system is the most efficient one, which is correct in this case because it has higher COP. Okay, so higher COP and higher in terms of more efficient systems. So splits ACs are your decentralized system. So they would have higher energy consumption. So then we come to the concept of net incremental cost even for HVAC measures. So on the chart on the left shows percentage energy savings by HVAC measures, and on the graph on the right shows the net incremental cost in rupees per square meter. The bar in yellow shows energy cost savings annually, okay, in electricity, and bars in blue here shows the energy, those are the net incremental cost. So here the centralized system, VRF system, so these are your centralized system, VRF systems, air cooled, water cooled, and air cooled chillers, crew chillers, and centrifugal chillers. These are all centralized system. And decentralized systems are the split units with 3-star, BE 3-star, BE 4-star, and BE 5-star rating. So as you can see, VAV system with centrifugal chiller of COP 6.2 offers maximum energy savings of 19.9%, roughly 20%, and highest incremental cost. Again, because it would have cost for chiller, pumps, motors, etc. So they have highest incremental cost, and the energy saving is also again, when translated to rupees, it's roughly around 219 rupees. So these are sort of the measures, and these are sort of incremental costs for the same. The interesting part here is the negative incremental cost. Negative incremental cost. So the energy savings for unitary split units, that is B3, 4, and 5-star rated systems, are negative. That is the reason. That is because we, in the base case, what we have considered is a VRF system, which is more efficient as compared to these split AC units. Since that is the reason split units would have higher amount of EPI. So we have negative energy savings as well as, and since the overall system cost for split AC was roughly around 40 lakhs, and for VRF that was roughly around 64 lakhs in comparison. So the net incremental in this case is also negative. So yeah, and then we suggested to the client to go for centrifugal chiller with COP of 6.2 in this particular case, I would say. Yeah. Yashima, I would like to, and here you would start
Yeah.
the session.
Thanks, Mansi. So we have a few questions and I'll take them up. So one question is, what is the U value of roof and wall in the base case? So if you can go to your roof ECM slides, I think the roof U value was not clear.
Okay. So in my base case, okay, so I think here. Okay, so here in base case, what I have considered is I have not mentioned the U value, but it was typical your concrete roof, which would have U value of around 2.8 to 3. And my wall U values were roughly around 2.2. Those were both walls and roofs were both uninsulated in the base case, I would say. I hope that answers the question.
Right. Yeah. Thanks, Mansi. So we'll take the other questions after the session. I'll now pass it on to PC. Mansi, thanks once again for your presentation. I think the students will now be able to use the correct metrics for, estimating their cost in their reports. Thank you once again. If you can stop sharing your screen. Yeah. Hey, PC.
Hi. Sorry, let me get my video up. Yep.
Hi. Yeah. You can now go ahead and start sharing your screen.
Okay, let me do that. Where'd my Zoom go? There we are. Okay. Let me know when you can see my screen.
Yeah, we can see your screen.
Okay. So last time we went through how to model a VRF system, or what we call a direct expansion system. This time we look a little bit at centralized systems. And I guess when I say centralized, I'm talking about chilled water type systems. So whether the chiller is air cooled or whether the chiller is water cooled, we're talking about chilled water systems. These systems have got one chiller object. That chiller object will produce chilled water. That water is pumped around, and typically it's pumped into an air handling unit, and there's a cooling coil in there. Hang on, let me pick up a presentation slide so we can look at it a little bit more carefully. So if you look at this slide, you can see that this is the room you are conditioning. This is cold air being delivered to the room, and that cold air is being made by passing air across a coil. And in this case, the coil is made cold by water, chilled water, which is being generated by a chiller. So you have refrigerant, but it is contained in the chiller. It's sealed in a hermetically sealed series of vessels. So in between the condenser, the compressor, evaporator, expansion valve, all this happens inside the chiller object. Okay. Now, in a VRF type machine, it too has a compressor, and that compressor also gets warm when it is doing work. So in the chiller, what happens is when the condenser gets warm, we actually pump water from a cooling tower into the condenser side of the chiller and cool the chiller down. Okay. In the case of a VRF system, we use air. So we blow air by a fan and pass it across the condenser coils. That's a less efficient way of cooling the condenser. That's why water-cooled chillers, if we use them, they are more efficient, because what you do is you have a cooling tower, and a cooling tower is like a big shower. So you spray water from the top, and as you spray water, some of it evaporates, and when it evaporates, it cools the rest of the water, and that cooler water is used to cool the chiller down. Okay. Now, in a dry climate, you can get quite cool water in the cooling tower. So actually, water-cooled chillers work really well in a dry climate. Okay, but then those are the climates where water is difficult to find, so sometimes that's not the best strategy. But anyway, so I've got here a fully plumbed system, which I wanted to show you. If you compare that against that PowerPoint presentation that I showed you, it's very similar. Okay, we have a zone, we have an air loop, we have a chilled water loop, we have a cooling tower or condenser water loop. And if you look at the model here, it's very similar. Okay, so I've got the zone, or rather a zone group, because there are many zones inside that zone group. We only see one zone in the zone group, but if you open it up, you can see all the zones that are being catered for. And those zones are being conditioned by, if you want to do cooling, there is a cooling coil here. You're blowing air. So there's some outside air that you're bringing in. and you're mixing it with return air coming back from the zone, making that air cold, and that cold supply air is being sent to the zone. Okay. So obviously, to make that cooling coil cold, you have a chiller. The chiller has got a pump. It's got a controller which determines how to set the chilled water temperature. Now, while the chiller is doing work, it gets warm. In this case, it's a water-cooled chiller. So we have a cooling tower. That cooling tower is connected to the condenser side of the chiller, and you have a pump which pumps water through the cooling tower, sprays it down, picks it up, and then sends it, the cooler water, to the chiller. So it all sort of works well. Now I've shown a boiler and a heating coil, both in the AHU, and in this case, we're using a variable air volume, VAV system. And in the VAV box, we have what's called a reheat coil. Now that's not always there, but in cold countries, you have a reheat coil. In India, we probably wouldn't use a reheat coil, okay? In India, we may not even use a boiler because we don't really have too much of a cold problem, particularly in office buildings. But I've just shown it there for completeness sake. And again, these two coils are hot water coils, and there is a controller on the boiler loop. There is a pump on the boiler loop, okay? So how do you build this when you're doing design builder? Well, there's a number of ways. And at this point, I would encourage you, I don't know if you guys have gone and seen them, but last time I showed you, there were 2 webinars, and I've been watching them. They're quite new. So they're actually quite an upgrade to what was on the YouTube channel, okay? And I do suggest that you go and watch them because they handle in more detail than I can in this time frame. The first one you should watch is this modeling HVAC systems from concept through to detailed design. So he takes you through how the simple HVAC model works, and then he takes you to the advanced HVAC system model, which is what we're talking about today. So those are quite good. I really do suggest you should go and watch that. Anyway, so to give you a flavor, okay, the easiest way is to start with a template, and Design Builder has lots of templates, okay? So if I decide I want to put a new system on, I can actually look at the templates that Design Builder has. And you will find that it has quite a few templates available which you can search from, all right? If you are doing any of the ASHRAE 90.1 systems, they're actually already built in as templates. So you can pick one of them if that's what you're aiming for. If not, there's a series of systems here. We're interested in a VAV system. We want a water-cooled chiller. We want an AHU, okay? So the idea is to pick something that is close to what you want, and then you can modify that to get exactly the system that you want. Now, if you were interested in heat recovery, then there's one here with heat recovery. If you were interested in doing full humidity control, there's one here that has got a full humidity control. Americans do a system called dual duct. There's one of those as well. So there's quite a few different kinds of templates available. So I'm going to pick the VAV with reheat and a water cooled chiller. So if I pick that, okay, it will show me what I'm going to get. So in this case, you can see it's very close to the one I've got. It's got one chiller, one AHU, one cooling tower, one boiler, one AHU, and in this case, chill water coils, hot water coils, and also reheat coils over here. So it's very similar to what I've got. Now, if you go next, then it'll actually put that there. So you're starting with a single chiller, all the zones will be on it. You get the option of putting out, taking off the zones you don't want to condition, and so on. I won't install it now because I made quite a few changes to the basic template, and we can go through some of that. And I'll also show you how you can add things to this type of system. So if we start to examine what's here, you can see that there are a number of loops, all the loops we talked about. Okay, so if we start with this chilled water loop, you can see here all loops in Design Builder reflect what Energy Plus does. And Energy Plus talks always about a demand side loop and a supply side loop. Okay, so if you go and look at this chilled water loop, you will see that there are actually two parts to it. So the question to ask is, what is demanding chilled water? Okay, that's the demand side. So in this case, what's demanding chilled water is that cooling coil inside the HU. That's the only cooling coil that we can see. Obviously, if you got more than one AHU, then you'll have more than one cooling coil. But that's the demand side. And the supply side is whatever is producing that chilled water to supply to that coil. And if you look over here, you can see that there are three components in that supply side. There's the chiller itself. There is a controller, what's called a set point manager, and there is a supply pump. Okay, so you can edit at any level in most things in Design Builder, which will reflect what Energy Plus does. So at the loop level, you can edit what the whole loop does. Okay, so in this case, there's a chilled water loop. It's variable flow. It's sequential. The design output temperature is 6 degrees. The delta T, so between the inlet and outlet, is 6 degrees. So this is what mechanical engineers would call a 612 chill water loop. Okay, so it's designed to produce water at 6 degrees, and at full load, when it comes back from the building, it will be 12 degrees centigrade. So it's working between those two limits. Okay, then you have something called plant equipment operation. So depending on how many chillers you have, you can schedule them. So you can actually size them and say, okay, this chiller should work in this range. The second chiller should come on at this range. The third chiller should come at this range, and so on. Okay, and if you go and read up something called swing chiller operation, you can actually set it up to do that. So that what it does is, if you've got a low load chiller and another main chiller, then you can set up the low load chiller to handle all the lower loads, then the main chiller to handle the next set of loads. And then when the main chiller runs out of capacity, you can bring back the low load chiller to add to both the capacities. Okay, so that's how you control at the loop level. Now, if you go and look at the chiller itself, you can again do a whole bunch of edits at the chiller level. Okay, so here you can specify COPs, you can specify reference values for the COP. You have, if you know your chiller and you can work out the curves for it, you can actually nominate a series of curves so it will model how your chiller is working. Now, one way to think about it is that there is actually a whole bunch of chillers already pre-programmed inside Energy Plus, which is reflected by Design Builder. These are not the latest chillers that you can get, but they are one generation older, but they're still pretty efficient chillers, okay? And you may be able to find something that's useful. They come with all the capacity curves already built in, okay? Some things you should be careful about is chiller manufacturers always give you extremely optimistic details about, oh, our chiller will work down to 5% of capacity or 10% of capacity. While that might be true, it doesn't help stable operation in a chilled water circuit. Typically, most engineers don't like to see chillers go below 20% of their capacity. If you do, then it starts to do hunting. It'll stop and start and create a very unstable kind of operation. So that's the difference between what you get as a simulated output and what actually happens on the field. So if you want to get results that are closer to what is possible on the field, these are the things that you need to be careful about. Okay. Similarly, you can set different ways of controlling how the chiller produces that or aims for that temperature. Hold on, I think. Yeah. So in this case, it's a very simple schedule. I've asked it always to aim to produce 6 degrees centigrade water, but it needn't be. You can actually have 2 or 3 kinds of managers. You can ask it to follow outside air temperature and provide some set points as to what they should be. There are other ways. You can have a dual set point, so the chill water is always working between a high point and a low point. And what you'll find is that Design Builder and Energy Plus will give you the most common industry standard managers for each component. They're reflected as you go through. Obviously, it means you need to understand your mechanical engineering a bit. It's good to get a good mechanical engineer who has HVAC design experience involved. So for example, here's my chilled water pump. Okay, so here I'd be looking for what is the design pump head. So I've got here 200 kPa. You may want to check what your engineer designs to. What is the motor efficiency? What's the kind of motor control and so on, okay? So these allow the program to simulate how the system will work. Now you can do the same thing at every loop. So let me just quickly go through the air loop, okay? So the air loop is your AHU supplying to the zone, okay? Now, again, same sort of thing. At each level, you get to edit certain things. Okay, here you can decide what is the flow rate for heating. What's the, normally VAV systems will come down to their lowest flow when they go into heating mode. As you go into the components, again, you can edit them. So at the AHU level, you can set up all kinds of things. Usually, if you want a return air fan, or if you don't want one, you can untick that box. You can add economizers. I've got a fixed dry bulb economizer here. The economizer maximum temperature is 23 degrees. So when the ambient air goes above 23 degrees centigrade, the economizer stops working. Okay. What's an economizer? Well, when the air temperature is low enough, it will not use the compressor, or it will use the compressor less, and it will use air directly from outside. Okay, you can set up humidity control. You can set up demand control ventilation. I suggest you don't do that unless you really, CO2 controls are not your most sensitive control mechanisms. But anyway, there's heat recovery mechanisms. So if you're working with things like an outside air system and you want heat recovery, you can put heat recovery systems here. You can put plate heat exchangers, rotary heat exchangers. You can work with both sensible heat and latent heat. So if you're dehumidifying using rotary heat exchanger, you can specify over here. And when you do, suppose I put that on, you will find it'll be reflected in the AHU. So here's a heat recovery component that's just come on. Okay, so I'll remove that for the present, but those are available for you to put in there. Now, you can go even further. You can actually go inside and edit up to at the fan level. So at the fan level, it'll ask you for what is the total pressure that it has to generate. So that's not your external pressure. This is your total static pressure. Okay. What is the fan impeller's efficiency? What kind of curve is it working towards? So for example, if you've got a variable speed drive fan, you might want to give it an appendix G curve. Okay. Those are things you can again look at. You can go in that AHU and actually look at the cooling coil, and you can sometimes do some edits on that. I suggest you don't go down to that level unless you are very clear about what you're doing. So there's your air loop. Similarly, the condenser loop has got the cooling tower, and as before, you will find that it comes in a demand and supply side. And at the supply side, there's a cooling tower, there is a pump, there is a controller. Okay. Now, these are all the loops that deal with all the mechanical equipment. The zone representation is now if you think about it, you've got two representations. You've got the representations from the architect side. So that's where you're looking at U values and what's the equipment load and what kind of glass you have, what's the solar heat gain coefficient, etc. But here you're looking at what is actually, how is the air conditioning system represented at the zone level. Why is that important? Because typically when we start to talk about air conditioning systems, a lot of the talk is about what's happening at the zone level. So for example, when you talk about VAV systems, this is what it is. You have an AHU, you have a VAV terminal. From the VAV terminal, you have ducts, which are attached to diffusers, which are putting air into the zone. So at the zone level is where your VAV box is. If you had other types of systems, for example, if you started to talk about, say, I won't talk about passive, but at least active chill beams, for example, okay? Again, it's what's happening at the zone level. Okay, you have an active chill beam. Essentially, it's a cooling coil, which is fed what we call high temperature chilled water. and primary cold air. And there is a induction that happens across the cooling coil. Okay, so you have two kinds of cooling, one by the primary air, one by the induced room air that goes across the cooling coil. So again, that's happening at the zone level. If, for example, you start to talk about an underfloor air conditioning system, again, it's happening at zone level. Something is in the zone. So essentially, you may have something happening underneath the floor, and that's being supplied to the zone level. That's why the zone level is so important. Okay. So if you go back to our design builder representation, the way it works is that if you make a change in one of the zones that's in a zone group, you can reflect it across the entire zone group. Okay. Now, what does that mean? That also means that if you start looking at a real project, like a real building, let me show you one. Here's a real office building, okay? Something that we worked on a few years ago. Now you will see here that in this building, these rooms are meeting rooms, okay? These are open area workstations, okay? So how would you air condition? Well, you can't have a pure air conditioning system in most places. Most buildings have some mix up, okay? So in this case, what is happening is that we are using VAVs and air handling units to condition these open plan workstation areas, but we are using chilled water fan coil units in these meeting rooms, okay? So in the AHU, there is a cooling coil that takes care, they're big. So big fans, big AHUs, big cooling coils, they're taking care of these open areas. But these ones have got smaller fan coil units sitting on the ceiling. There's a cooling coil, there's a fan. You can switch these on and off as you need them. They needn't run all the time. Okay, so typically in real buildings, you have this kind of mashup of different kinds of systems. You can do that in Design Builder as well. So what you do is you pick up some of the zones. So what you can do is you can release some of these zones and put them onto a second type of system. Okay. So those are the kinds of things that you can do. And if you watch that detailed advanced HVAC webinar, actually he goes through that in some detail. So I won't spend too much time on that. What I wanted to show you was something that probably we haven't discussed so far. Okay, and it may be difficult for you to find information about it, but it's worth thinking about it. If you have your system, okay, in this case, how will you make this system efficient? Not by changing the U value, not by changing the building envelope characteristics, but by looking at the system itself and by improving it. What can you do to use less electricity? That's the goal, okay? What are the things that use electricity? Well, your chillers do, your cooling tower, fans, pumps, supply pump for the chilled water system, the fan motors here, they use electricity. So these are the things that are going to be using electricity. Your cooling load doesn't change. Your total cooling load is the same. If you've got a building for which you've got a particular kind of operation, for which you've got a particular kind of materials, U values, different kinds of windows, lots of roof insulation, there's one cooling load for it, your maximum cooling load, which has been calculated when you did your load calculations. But how do you go about trying to address this load in an efficient way. Okay. Now, a couple of things that I would do. Okay, the first thing I might do is to say, well, if I have a chiller, if I have one chiller and I have a 1,000 kilowatt requirement, okay, say 100 tons, if you want to think about it in tons. If you have just the one chiller of 100 tons, when you need, say, 10 tons of cooling or 20 tons of cooling, then your 100-ton chiller is working at a very inefficient place. It's like a car, which if you run it at an optimum speed, say 40 or 50 kilometers an hour, would use quite low amount of fuel. But if you went into the city, which went into Bangalore in the middle of office time, you can barely make 5 kilometers an hour. At that point, you're using a lot of petrol. It's the same thing for the chillers. In the inefficient part of its curve, if you use it more, then it will use more energy. Okay. So I might think about, okay, if I split the chillers into two, if I have two chillers, one which is slightly smaller, one which is slightly bigger, okay, will that help? And then you can look at the variation of the cooling energy across the year, and you may be able to pick two chillers, two sizes, where they run at their their optimal parts, and you'll see the energy use drop. You won't see the cooling load change very much, but what you will see is that your pumps and your fan energy start to reduce when you optimize these sorts of things. In this case, you can also think about how you break up the zone groups. Okay. Why? Because if you have zone groups that are looking at the perimeter zones, okay, the zones that are at the edges of a building. So if I went and had a look here, then depending on which way you are facing, okay, so in India, you will be getting sun on the south side and the east side on the west side. You won't be getting that much sun in the north side. You won't be getting any sun in the internal zones. So one of the things I might do is to first put the internal zones in a different AHU. And there I can then start to give it less cold air, okay, and control it differently. And then you will find that the energy use may come down, again for pumps, may not be for fans, okay. So those kind of options can be explored, where delivering the best outcome from your HVAC plant and system needs to be thought about. Now, that has nothing to do with what Mansi was sharing, which is basically looking at how the building determines the load. So obviously, first you want to do that, optimize your building envelope. Then you want to optimize your HVAC system. For that, you may need to work with a mechanical engineer. Okay. I don't think there's too much else to show you. You'll have to try pulling your systems together. And the second seminar, that advanced seminar that I was talking to you about, that actually shows you how to connect components and so on. Okay. For example, I can show you, we'll do one quick example. We can basically split up this into, as I was saying, maybe we can put a second AHU where we can put all the internal zones onto one, and we can put all the perimeter zones onto another one. So to do that, what I will do is I will make myself a second AHU. So I'm going to take that, right? I'm going to clone this. So it's easy enough to do. Clone the selected object. So here I've got another AHU. Okay. Now I need to have a second zone group because I want to condition some of the other zones on this zone group. So let me escape out of this. And here I'm going to clone this zone group and click on the middle of that, bring it here. So here I've got a second. Okay. Now, obviously I need to connect some of these things, but sometimes you'll find that I may need to have to assign some zones to it before I can start working on it. So first thing I'll do is I will release some zones from this zone group. Okay. The ones I want to release are these internal zones. So I'll take off these internal zones. Okay. And I will add them over here. So I don't want the unconditioned. I only want the internal zone. Because I release them in the other one, they'll show up here. Okay. And what I can do is I can call this zone group my internal zone. Okay. Here we are. Now I can rename my air loop. I will just edit that. And let me call that also my internal zone. Okay, that's good. Now I need to connect these two together. So first I need to connect the air loop and the zone loop. So I'm going to select one, press Control, and then there is a connection icon here, and it will connect for me. You can't do everything, but there are some things that it will automate for us. So here you can see that it's connected the air loop to the zone group. Okay. Now my coils are still not connected. I need to connect my chill water coil to the chill water circuit and the hot water coils to the boiler circuit. So let's try that. So if I go to the chilled water loop, and if I go to the demand side, I can connect it. Okay. So there's a connection loop here. Let me see if it'll automate it. I'm not sure, but it's worth a shot. Let's try this. If it doesn't, I'll show you the manual way. But let me try. No, I don't think it likes it. Okay, so let me do it manually. You can do anyway. If you look at some better examples than mine, you'll see that people make some nice drawings, and that's good so that it doesn't get complicated. I'm just going to be rather brutal about the way I draw this. Okay, so my chill water circuit's connected. Now I need to connect my hot water circuits. I haven't made any changes to the chiller and the condenser water side of things, so I don't need to worry. Here we are. So what you'll notice is that every time you connect something on a loop, it will automatically give you another connection point. So here we are. And now connect to the other side of the loop. And as you can see, it's giving me more points as okay. So you can run it, but at this point, it's got exactly the same control strategy as the first one. And I think I'd like to change that. Now, that's not straightforward. You've got to actually go into the AHU and then give it a different temperature set point because it's an internal zone. You have to do some calculations and then figure out what is the supply air temperature you want to set it at. And what you can do, what you'll find is that if I look at the set point manager, okay, so here I've set it to go from 12 degrees to 18 degrees, okay? And that's what we would typically do if there was no other, there was only one. In the internal zone, I can actually take the temperature up a little bit. So instead of 12 to 18, I can ask it to do from 14 degrees to 18 degrees, okay? So that is something that I might do. And then once you've done that, you may find that it will work easier and control temperatures easier on this system. Now, again, those are a few engineering things that you need to talk to your mechanical engineer about, okay? And what you will find is that the system is stable and can become more efficient when you do things like that. So those things are all available to you. You can do many different kinds of systems. I think in the video, they actually talk about radiant panels. So they talk about both heating and cooling radiant panels. The way that you model them in Energy Plus and Design Builder is you also have to look at the construction because it kind of assumes that your radiant surface is either your ceiling or your floor, and you have to change that as well. And there's a little bit of an explanation on that, okay? Now at each point, now for example, what we can do is I can show you one more thing before I close off. And that is that, for example, the zone group that we've just had, we can even use a different kind of system. We needn't have a VAV system. We can probably say, if you wanted to, we could add a chilled water fan coil system here. So I can add a chilled water fan coil system, delete the VAV system with a reheat, just put a normal constant velocity inlet in here. And then what will happen is that whatever I put in this zone group, it will replicate to all the zones in that zone group. Now I haven't connected it, but you can see where I'm going with it. Okay, now in this case, I've got a chilled water and hot water coils in the fan coils, and I will need to connect those. So if I wanted to do that, it's pretty straightforward. As before, you go to the chilled water loop, you go to the demand side, it will show you what can be connected. So I can connect that. And once I do one, it will basically do the same for all zones on that zone group. So that way it's quite easy to do. So as soon as you have a zone group and you have connected one setup, it will basically, as I said, I'm going to do this without thinking about how the pipes are crossing. but you can certainly draw a more intelligent version of this when you work on it. So here I've connected that, and on the hot water loop, if I do the same, then this model will be ready to run. Again, you have to look at the controls a little bit, but other than that, it's basically ready to go. Okay, so that's the way you would basically set up different kinds of systems. So what I've got now is I really have a water-cooled chiller with a cooling tower to cool it. I've got two air handling units. One is doing all the perimeter zones with a VAV system. I've got another air handling unit, which is doing chilled water fan coil units for all the internal zones. Okay, so those are ways to do that. You needn't use the chilled water system at all. You can have a separate zone group. You may be able to, you may have a few zones which are not connected to your main chilled water system. It may be just a series of split systems. You can model all of that. Okay, so you can do pretty complex air conditioning systems within this. I think I've got about 15 minutes. Let me just quickly show you a couple of slides which I use for teaching when I'm teaching students. And I just wanted to show you this because you can start thinking about how to put air conditioning systems together. Okay. So at a very gross level, your sort of Rolls-Royce air conditioning system. Okay, on the roof, you have a chiller, and it's a water-cooled chiller, so you have a cooling tower. And you have big centralized air handling units. So air handling units in a plant room in the roof. They blow air all the way down the building. There are branch ducts at every level. And then those branch ducts may be supplied by VAV systems, active chill beams, fan coil units, whatever. But the AHU is sitting centrally on the roof. That's number one. At the next level, you can keep your chiller on the roof, your cooling tower on the roof, but instead of having big air handling units which pump all the way through the building, you can actually have smaller air handling units on each floor. So floor by floor air handling plant. And those things can then again supply a different kind of zone terminal unit. So you can have VAV boxes, fan coil units, whatever you wanted to do. Okay, there's another one. So here's a building that we did, floor by floor air handling unit supplied by VAV systems within the zones. Okay, you can go even finer. So if you are, say, in a university building and there are lots of cubicles, you can still have your chiller on the roof, cooling tower on the roof. You can then have a fan coil unit at each room. Okay, so you still have a centralized chiller, centralized cooling tower, but you can have fan coil units in each room. So for example, for hotels, this is a very efficient solution. So only the fan coil units that are occupied, when they're occupied, call for cooling. You only need to provide chilled water. As long as you've got a variable speed pump and you've got two-way valves everywhere, the pump will speed up and slow down. Okay, so you can, as I showed you before, you can mix it up. These are open air workstations, VAV boxes, centralized AHUs on the roof. These are fan coil units for each room. Okay, so that kind of thing you can do. And there are other systems, right? I won't go through them, but there's water-cooled package units, air-cooled chillers, etc., etc. But something to think about. Once you know what you're doing, it's quite easy to replicate that in Design Builder. Not so easy to think of the control strategy, which is practical. That you may need to speak with a mechanical engineer who has experience with air conditioning design. Okay. And you may need to have some discussions about what is the best type of air conditioning system for the type of building, the type of usage. You may have more than one air conditioning system in the building. And typically in India, you almost never have a fully air conditioned building. Some parts are air conditioned, some parts are not. So how do you combine the two? Mixed mode buildings are, in dry climates, they are fine. In humid climates, they're a bit more difficult because when you open up the building to allow external air to come in, it brings with it humidity. And the next time you turn on the air conditioner, if you're not careful, temperatures of surfaces will drop below the dew point. You'll get condensation. And the worst case scenario, you might start to get rain inside the building. But yeah, you need to be a little bit conscious about that. No problem in dry climates, but in humid climates, you need to be a little bit careful about how you do that. Okay, I think I'll stop talking, and if there are any questions, we can pick them up now.
Sure. Thanks, PC. We do have a few questions and I'll take them one by one. So first question is, can you share some information about radiant cooling systems for energy models?
Yeah, I mean, look, radiant systems, they're basically you're doing very similar to what they call chill beam systems around the world. You are using an air handling unit to provide air, and you're using water at a slightly not so cold temperatures to do some of the cooling, convective cooling. They call them radiant cooling systems, but they're really doing more convective cooling than they're doing radiative cooling. Okay, they do part radiant and part convective. Now, if you want to see that, let me just share my screen.
Yep.
So you can, within Design Builder itself, I'll show you. Yeah, you actually do have access to radiant. Oh, that's the high temperature radiant one. There is another one where you can put a radiant surface in there. This one, I think. Yeah, so you can actually put radiant panels in there. Okay, so they can be either the floor or the ceiling. You can connect them to the chilled water loop and the hot water loop. If you don't want, they come as one unit. If you don't have hot water heating, just put a dummy boiler in there, switch off the boiler, and you won't get any radiant heating. Again, as I said, watch that other webinar. He actually shows you an example about how he uses the radiant cooling system. Obviously, in this case, you don't need a VAV box here. You just need a normal inlet. So I would put a constant volume air inlet without any reheat. And then whatever conditioning you want to do for the outside air, you can actually connect that and you can devise how that works. So what you need to do is then work out how this air handler is going to provide, what kind of air do you want this air handler to provide? Okay, you got to combine your radiant system with your air handling system. If you want In some cases, you are calling it a dedicated outside air system, but that's a very specific term. But you need to think about how you are controlling the air temperature, because now that's independent of the radiant system. Okay. So in some cases, people use what we call neutral air. So you're always sending in air which is about 21, 22 degrees centigrade. Again, as I said, in dry climates, these systems work really well. In humid climates, you have to be quite careful, particularly the air that you're bringing in. You need to dehumidify that before you bring it into the room. Otherwise, you can drop below the dew point temperature for those radiant surfaces. In that case, you will get condensation on those panels. And as I said, extreme cases, it may rain. But I know there's a lot of radiant systems in Hyderabad, Bangalore, Ahmedabad. These places are dry. They will work really well. You can decide on how much load the air side will take and how much load the water side will take. So again, you need to do some calculations before you draw these systems in. It's difficult to auto size these systems because you need an engineer to work out the splits and then work out how to do that. But modeling them is not particularly difficult as long as you know your air conditioning. Hopefully that's handled that question.
Right. Thanks, PC. I have also shared the link to the webinars that PC referred to on chat. So you can go ahead and, look at the webinars on the Design Builder website. Moving next. I think you have already answered this question, but I'll just say it out. How can I add more AHU in VAV system? We did
I think
discuss
we
this,
just
right?
did that.
Yeah. All right. We can move ahead. Next question. Can we do this kind of detailing of an HVAC system in other softwares like eQuest? Is that possible?
eQuest is a derivative of what used to be called DO2, right? And what they have is they have a series of standard systems. So as long as you're using one of their standard systems, you're okay. But if you want to, combine systems and sort of make it sort of flexible, it's a bit harder in eQuest. Design Builder is much more, and the graphic user interface for Design Builder is so much better than DO2. I used to use DO2 and eQuest till 2006. Then I shifted across to Energy Plus. Actually, I shifted to Energy Plus only because I could see the potential of Design Builder. So I would suggest that that's probably an easier option.
Right. Yeah. Thanks, PC. Next question. It's not a complete question. It just says refrigerant used for chiller modeling. I am just anticipating that it means that is a refrigerant used, when we do chiller modeling.
Okay,
Right.
so there might be the guy who's asking the question might have two potential questions. I'll try to quickly answer them. One is, if you're asking me, are we modeling the refrigerant circuit? The answer is no. We are modeling a correlation of the compressor's map. So basically we are saying, okay, if these are the conditions, then the compressor will use this much electricity, and that's what we are modeling. Number two is that does a chiller use refrigerant? Yes, absolutely. But you don't see it because it's all contained within the chiller. In contrast, when you use any sort of a split system or a direct expansion system, VRFs, split systems, whatever, then you're not pumping around water, you're pumping around refrigerant. Okay. What is the implication of that? If your strategy is to reduce greenhouse gas emissions from your project, then you need to start thinking about direct emissions from leakage of refrigerants. Why is that important? Well, the typical refrigerant that is being used in VRF systems or split systems, and you can go and have a look at that, they use high pressure refrigerants, R410A, those kinds of refrigerants. They've got what we call very high global warming potential. So if you lose 1 kilo of this high pressure refrigerant, it is equal to, in some cases, 1900 kilograms of CO2, greenhouse gas emissions. Okay. So all the energy efficiency measures that you might have taken may be lost because you will lose refrigerant because of leakage. And when you have a direct expansion system, you are connecting these joints on site. Okay. Unlike a chiller where everything is inside the chiller, it's factory made, you never see the refrigerant circuit. So it's not a question about if that refrigerant will leak, it is when that refrigerant will leak. Now, what makes it worse is many of these refrigerants are blends. They're not a single refrigerant. So if you leak, if your refrigerant leaks, then your technician will come in, but he cannot refill it straight away. He actually has to decant the rest of the refrigerant and refill it. If he can't find the leak, which he more than likely won't be able to, he'll just refill it and go away. Okay, and over time, this will leak again. So I would encourage you to start thinking about direct emissions from refrigerants as well. In some countries, in some European countries, they are now banning direct expansion systems beyond a certain capacity for two reasons. One, this direct emission, and number two, because there are concentrations of refrigerant in the occupied space, and they're not really healthy for you. Okay, they're not really poisonous either, but they're not particularly healthy for you. Now, we're going off slightly on sort of different track, but very quickly, the industry has responded by finding some new refrigerants which have got lower global warming potential. So they're using something called R32. Okay. Global warming potential is not 1900, but it is 600 kilograms CO2. Big difference, 1/3, but still pretty high. But the problem with R32 is that it is higher flammability. And in Australia, you can't put that inside an occupied space. Okay. So they are coming up with things called hybrid systems. You may want to look at some of that as well. Okay. You can model them in Design Builder. The water-cooled VRF systems is what we call them. So in that case, then the refrigerant is not spread that widely, but it is still something to be aware of. Okay.
Thank you so much, PC. Mansi, I am seeing that you have been answering questions. You've been typing out answers. I'll just take a couple of these questions. I think they're important questions. So if you can talk a little bit about them. The first question is, what do you mean by negative energy savings? If you can please elaborate on that.
Sure. So I would like to share my screen. It would be simpler.
Okay,
You
let
know?
me, yeah, thank you.
Yeah, I just stop PC's screen share.
Sure.
Yeah.
Can you see my screen?
Yeah.
Yeah.
Perfect. So here in this case, we have negative energy savings. Okay, here in the split unit, I was explaining that, your energy savings are in negative 23.9%, 16%, 20% Why would this would happen is, in this particular case, the base case which I have considered is VRF system. VRF system here has the COP of 3.8. When you go from COP, VRF system, which is more efficient as compared to split unit, which has COP of 3.8, when you go back to COP of 3, you are going to actually increase the EPI, energy consumption, annually. So that is the reason we'll have energy savings in negative, because the base case is more efficient as compared to split unit here. But this was just to show to the client that, this is the possibility. So that is a big no. And they should go for more centralized systems. I hope that
Right.
answers the
A
question.
follow-up. Thanks, Mansi. A follow-up question on this. Can you please explain how was the net increment value negative in the first slide?
Okay. Net incremental in the first slide. Here, is this the slide they're talking about?
Net incremental value is...
Yes. So net incremental
the one.
cost in this
Yes.
case is negative.
Yeah.
Okay. So I'll tell you why. So here, when you have roof insulation of 0.9 watt per meter square, you are going to have cooling capacity savings of 4.15 lakhs. So cooling capacity saving is nothing but reduction in system sizing. So say if you require 200 TR of refrigeration, which is in this case, base case, with U value of 0.9, you would require refrigeration of 172 or so. Okay, because here we are reducing by 8 TR, right? So you would require 172 tonnage of refrigeration, and that would reduce the first cost of HVAC system. If you would require, say, 5 lakh rupees in this case, this would significantly reduce. So here in this case, the saving is 4.15 lakh in system sizing, saving in system sizing. And so the net incremental cost is negative, because there is again sort of energy savings because of the roof measure and annual electricity bill. So a net incremental cost is negative here, because this is the difference. I think this is the difference between the incremental cost and your cooling capacity savings. I hope that answers the question. Yeah, Shima?
Yeah, great. Yeah, thanks, Mansi. All right. One more question, Mansi, I would take up. For an educational building which has only admin areas as air-conditioned spaces, will a VRF HVAC systems be suitable?
Okay. So VRF system, you can link up multiple indoor units with a particular outdoor. So that is again a centralized sort of a system. The tonnage of refrigeration varies from 30 to 43 tonnage of minimum of 3 to maximum of 40 or higher. Even we look into various companies like Daikin and others. So you can choose this option if you want one particular outdoor unit and connect it to multiple indoor unit. So I would say it can be deployed in various kind of spaces, and school admins can be one of them. Sure. It depends on the how much tonnage of refrigeration actually is. I hope that
Great.
answers the question.
Yeah. Thanks, Mansi. We're getting in a few more questions, so I'll take them up. PC, one question for you. Will we see the use of artificial intelligence in HVAC systems?
I
your
hope so.
opinion?
They're going in everything else. I think we are seeing what is called diagnostic solutions, which are digital. So basically, we do have systems where they look at all the parameters, and if one parameter is out of whack, then it will inform the user. So that is already being available. In terms of artificial intelligence, typically, if you have a good database, then you can teach a machine to look at data and analyze it. That has been the trouble to date, because no two buildings are alike. Every building is slightly different. So it's been difficult to get like a robust set of data to feed to a machine learning type algorithm. But I'm sure that people will find ways around it. It's only a matter of time.
Right. Yeah. Do you want to add something to that, Mansi? Okay. I think you're saying no.
Yeah, I was on mute.
All right.
Yeah,
Okay.
it's on.
I think we have one more question, which is what is the maximum tonnage available in VRF systems? Mansi, are you
Interesting
aware
question.
of?
Yeah,
The
so
question is, what is the maximum tonnage available in VRF systems?
okay, so that roughly that is different for various
Right.
companies. So Courier has something, say Daikin has a whole VRV systems which they have generally from 10 to 100 TR. However, they can be, clubbed together. So then there are two sort of VRF system in a particular building. So that you can have a combination of, I would say.
I
Right.
think that if I can add to what Mansi said, when your capacity for tonnage or refrigeration gets beyond a certain amount, somewhere there'll be a cost benefit ratio where you may want to then start going into a chilled water type system instead of a VRF system. Because even though you have outdoor units, you'll start to get like a forest of condensers on the roof. And beyond a certain point, probably there's a cost crossover where you might start to think, okay, this is no longer VRF territory, this is more chilled water territory. I don't know what the numbers will be, but in terms of kilowatts, now that's 3.5. So we're looking at about 200 tons. By the time you get to 150 to 200 tons, I would be saying, in my opinion, you should be seriously considering looking at chilled water systems. But that's, again, it's in each country, it's different. Each engineer has his own way of looking at things. Ultimately, it's probably worth using a energy simulation at that point to make that decision as well. I think Mansi has illustrated that case very well. That's the kind of thing that we would use simulation to do.
I agree with you,
Great.
DC.
Thanks, PC. Yeah. So that brings us to the end of the session today. This was the fifth simulation training for this year, and this was also the last one. We have covered topics like climate analysis, building envelope, natural ventilation, and now a very detailed two sessions on HVAC modeling. And we hope that these have turned out to be helpful for you. A quick thing about the recordings, many people have been asking for them. So they are available on the learning management system. You can log in and access them. But the simulation trainings in particular have also been made available on YouTube. So you can go ahead and just, go to YouTube, look at Solar Decathlon India's channel, and you can access the playlist over there. I have put the link on the chat as well. And last thing about the deliverable 3. So it would be good that you look at the self-learning modules available on the learning management system before you start modeling. And as Mansi said, you will get an idea of, the kind of systems that are there, and what system would be the good for your project. So thank you once again. And we have a couple of more questions, so I would have to take those as well very quickly. Um, so one question is, for 130 tons in apartments, can we use 2 VRF outdoor units instead of one, or a chiller system in a composite climate?
Yeah, 130 tons, you're probably looking at about 4 VRF units or so at least. It's not just how big is the unit. It's like, what is the lowest amount of cooling that one outdoor unit can do in a stable manner. So, and then there is the question of, if you're looking at an apartment, there are other questions, more practical questions. How are you going to meter the use of air conditioning. If it is easier to meter by apartment, that may be different. If you've got a centralized system, then you've got to meter. How are you going to meter the chilled water usage, etc.? So those kind of questions start to come into play. So sometimes it's more commercial rather than technical. Would you agree, Mansi? Did you
I
have
agree.
anything to say?
I agree with you on this. So, however, what I have seen so far is, for mid-rises building from say G+3 or G+4 structures, each apartment, this is what I've seen in Ahmedabad previously, each apartment, if those are centrally conditioned, then they have outdoor VRF, single VRF outdoor. So rather than having multiple split, that is a better system. However, as you said, if they are for it to be regulated and for it to be, commercialized, it's going to be very difficult and tricky to understand. Metering would be
Right.
difficult.
Thanks, Mansi and PC. Another question about the artificial intelligence, PC. Very quickly, if you would like to share your opinion. So, do you think it can possess danger to job security of energy simulators and architects or designers?
No, I think AI is going to be dangerous for everybody, but we just have to do, what AI does is that anything that is done repeatedly will, of course, be in danger. And I think the next set of people, anyone who is doing basic documentation, lawyers who are doing basic casework, same kind of thing, I think it will all be there. So, but if you're doing something that is niche, that is good quality, that's difficult to replicate, then you are not in danger. So that's all I can say. We are using in our office now Chat GPT. So when we are writing reports, if we are, suddenly we are finding that, oh, we need a paragraph that says this, then we actually will get the core from Chat GPT and then we'll change it. But then the analysis we do, Chat GPT can't replicate. So that's what,
Great. Thank you for your insight on that, PC. All right. Thank you, everyone, for joining in today. All the best for your deliverable 3 submission. And we hope all our participants today, you're able to make it to the finals. Thank you so much. Bye.
Thank you.
Thank
Good
you.
night.
Bye.
Bye. Good night.